No.
Princeton, sorry.
Hey everyone, I'm Anders Miltner, and me and my collaborators worked on synthesizing bijective lenses. So I'm going to start off the day with a story called The Sad Intern, written by me and my collaborators. Once there was a happy undergrad who got an internship working for his favorite Linux distribution, Ubuntu. Ubuntu wanted non-programmers to start using Linux, so they wanted nice GUIs to edit those often used configuration files, like cron and apt. The happy undergrad cheerfully walked into his first day of work, and his boss explained the architecture to him. So he can't alter the Linux config files for backwards compatibility. The GUI will be hooked up to internal data structures, which are then converted into JSON format using automated serializers and deserializers. Then he wants to keep the ad hoc Linux config file and the JSON formats in sync with custom converters that he has to write F and G. After learning this architecture, he sat down and looked at the format he would hook up to the GUI. He quickly became very sad. The format was terrible. It was full of edge cases. At had a special meaning, but not if it was followed by exclamation point. Commas were tuple delimiters if the line began with a lowercase letter, and list delimiters otherwise. Is there no way for our hero to be happy? Is he doomed to write these horrible processors for these formats for the entire summer? We think synthesis is a solution, and we've developed a tool, Optician, for these types of synthesis tasks. So there's a couple ways that we can synthesize these types of functions. The first is that we synthesize F and G separately. So there is existing work on automatically synthesizing such functions. This work has ranged from general purpose synthesizers to synthesizers specifically for string transformations. Typically, the synthesizers built for string transformations perform better than general purpose synthesizers. If you're using a domain-specific language for string transformations, then a lot of undesirable functions are pruned beforehand, which makes synthesis a lot easier. Another option is to synthesize both functions at the same time. In an optician, we take this option. By using a domain-specific language where a single piece of syntax expresses both of the functions, we cut down the search space from 2 synthesis problems to just 1. Such domain-specific languages exist, and their terms express lenses. Focusing on bijective lenses, lenses comprise 2 functions. You have a put function, which operates by transforming from the left format to the right format, and a get format, which converts from the right format to the left format. So by synthesizing the lens E, we get both of those functions for free. How do we do this synthesis? We synthesize from format descriptions. So we ask a programmer to provide 2 regular expressions that describe the formats and also a suite of input-output examples into our tool, Optician. So then what we output is a lens that is guaranteed to map between the languages of the provided regular expressions and is also guaranteed to map satisfying the input-output examples. So our contributions are as follows. We've developed Optician, a tool for synthesizing bijective lenses. It operates by synthesizing in a language we developed specifically for synthesis, and then we convert the synthesized term in this custom language into a lens in a standard lens language. We've proven our algorithm correct, so not only will we return a lens that satisfies the spec, but also if there is a lens that satisfies the spec, we will return it. This involves proving that our synthesis language is equivalent to the original language. We evaluated Optician on a benchmark suite consisting primarily of maps between Linux config files and serialized formats, but also some more principled formats, some related work, and some custom benchmarks. Our tool was able to synthesize all of these benchmarks in under 5 seconds. Lastly, we integrated Optician with Boomerang, which is a lens language for expressing string lenses. And so in this integration, we can now express synthesis tasks as normal expressions. So I'm talking about lenses a lot. Let's go into actually what they are. And I'm going to go into lenses in the context of Boomerang, the programming used to express lenses between string formats. Our lens combinators come from Boomerang, and we're going to carve out a bijective fragment of Boomerang that we aim to synthesize. So I'm now going to work through this boomerang program line by line. The program describes a lens that maps from the first format, Stephen Cole Cleany, to the second format, Cleany Stephen Cole. The line I discuss will be highlighted in red and bolded. So the first line is just describing what is a name. It's just uppercase letter followed by any number of lowercase letters. And now we can get into our first lens, the identity lens. The identity lens takes in as input a regular expression describing what domain it operates on. So in this case, the identity lens performs the identity transformation in both directions on strings in the language of of names. So note also that Stephen is now highlighted in red and bolded. As I go through the program, I'll highlight in red the portions of the string the highlighted lens maps between. So now we have this issue with where white space is. So in the first format, we have Stephen followed by a white space, and in the second format, we have a white space preceding Stephen. So we want to perform some transformations, in this case the identity transformations, and then swap the locations of the data. This is done with the swap lens, expressed with the tilde combinator. Next, we can iterate that multiple times by using the iterate lens, expressed with a Cleany star. So now we do that transformation 0 or more times. Now we have this issue where we've got a comma on the right-hand format and not on the left-hand format. We can express constant transformations between strings by using the const lens, in this case between the empty string and a comma. Then we combine that comma lens with the Stephen Cole lens that we did before with the concatenation combinator. And finally, we use swap to swap the locations of the data. So our overall lens grammar is that we have the constant lens, which operates on two strings, the identity lens, which operates on a regular expression. We have the regular operators on lenses. One that I didn't go into is union, which performs one or another lens depending on the input string. And we also have swap, and we have sequential composition, which performs one lens's function and then the others. We also have a typing judgment. Why do we have a typing judgment? Well, there's a couple benefits to it. The first is that it specifies the languages that the lens maps between. So you know that this lens operates between, for example, ad hoc format and serialized format. We also want to guarantee that the get and put functions are well-defined functions and that they're also inverses of each other. And also, having a typing judgment is pretty useful for synthesis. So the typing judgment is a three-area relation. This would be pronounced E goes between R and S. So E is a lens term, and R and S are regular expression types. So E maps between the languages of R and S. So if we have E goes between R and S, that means the lens E provides two functions, the put function from the language of R to the language of S, and the get function from the language of S to the language of R. And we also have that those two functions are inverses of each other. We have three sorts of typing rules. The first are syntax-directed rules. These are rules where the combinators for the types are very closely tied to the combinators for the terms. So for example, in the typing derivations of concat and swap, the regular expressions of the subtypes are concatenated. We have composition, and we have type equivalence, which is to say if you have a lens between R and S, and you have two regular expressions, R prime and S prime, equivalent to R and S, then you also have that lens is well typed between R prime and S prime. Let's go into the syntax-directed rules, specifically in the context of synthesis. So recall that we're trying to synthesize lenses from the format descriptions, from the regular expressions. So we can see, oh, let's say we have these two regular expressions, R1.R2 and S1.S2. We can apply inversion on this and say, okay, we can break it into the subcomponents. I think it's going to be a concat lens. I know that I need to find a lens between R1 and S1 and R2 and S2. Then, after we have solved those subproblems, then we can combine their solutions and get the final concat lens. We can do the same thing for swap and union. We can also do it for iteration. So if we have two pieces of iterated data, we just need to find a lens between the base portions and then iterate that lens. We've got some base cases, so let's say we are looking for a lens between R and R. We can just synthesize the identity lens, and if we're looking for a lens between two strings, we can just synthesize the constant lens. Now let's go into one of the more complex ones in the context of synthesis, composition. So using the existing approach, we're looking for a lens between R and T. So we can break into the subcomponents, finding a lens between R and S and a lens between S and T, and then combine the solutions. But if you're paying attention, this S comes from nowhere. We just need to guess an S to find a lens between. And that's a huge search space because who knows what regular expression we need to put in there. So you might just say, okay, let's just remove composition as a rule, but composition is actually inadmissible. We need composition to express the same number of terms. So for example, there are certain permutations that can only be expressed using composition because we only have these binary concats and swaps. So our solution is to use an alternative language of DNF lenses. DNF lenses have no composition operator, and they are also equivalent to bijective lenses. And how do we maintain that they're equivalent without having a composition operator? We use arbitrary permutations instead of just the binary swaps. So our last rule is type equivalence. So again, if we have a lens between two regular expressions and those regular expressions are equivalent to other ones, then that lens is also well typed between those other regular expressions. So let's look at it in the context of synthesis. So let's say we're given this synthesis task, and we want to use our syntax-directed rules as before. So we look and we see, oh, the left format has a concatenation. Maybe I should use a concatenation lens. But when trying to break the right-hand format into a concatenated subcomponent, we can't because it's got an outermost disjunction. Similarly, on the other hand, we might say, oh, let's try to get an OR lens, but we can't on the left because it has an outermost concatenation. So in this way, the two regular expressions are incompatible. We can't generate a lens between these two types using only syntax-directed rules. But we can generate a lens between them. In particular, we need to replace the r.s or t with r.s or r.t. And after doing this, now the two regular expressions are compatible. We can find a lens between them using only syntax-directed rules. In particular, we can find the identity lens. So in this way, using type equivalence necessitates this need to search through equivalent pairs of regular expressions and try to find two that are compatible. This is the primary search, the primary non-deterministic search that we do in optician. But unfortunately, the number of equivalent regular expression pairs is huge. It's a very broad space, and it's very difficult to find all these equivalent regular expressions. So our solution to this issue is that we use an alternative language of DNF regular expressions. These are a pseudo-canonical form. So what it does is multiple regular expressions that were previously syntactically distinct now have the same syntax when in DNF form. But not all of the semantically equivalent regular expressions have the same DNF form. DNF regular expressions have outermost disjunctions followed by concatenations, followed by iterations, variables, and strings. So for example, the regular expression on the right is a valid DNF regular expression, but the one on the left is syntactically disallowed because it isn't disjunctions followed by concatenations. And we actually tie it in well with our DNF lenses that we create because these DNF lenses are typed between DNF regular expression pairs. So when we go into this issue that we had before, where we're searching for compatible regular expressions, this search is immediately pruned because the two types become equal when in DNF form. So now we performed some of this search through equivalent regular expressions automatically by normalizing. And in fact, all of the equivalences shown in blue are now syntactically equal. So if you would before need to process those equivalences, now they're just handled by having the regular expressions turned into DNF form. So we don't need to search through them at all. Unfortunately, there are still regular expressions that are semantically equivalent but syntactically distinct even when DNF form. For example, this one, you have epsilon or RR star and just R star. When in DNF form, they stay in the same way, but while they are semantically equivalent, they still have different DNF forms. So we still need to do some search to unroll the R star into epsilon or RR star. In this way, DNF regular expressions are only pseudo-canonical. Okay, let's go into the implementation. So we've got our regular expressions, we turn them into DNF form, then we use those and examples to synthesize the DNF lens. Then we just turn the DNF lens into a normal bijective lens. Let's look at the implementation of synth-DNF lens where the bulk of our synthesis goes in. We have two communicating synthesizers of DNF search and rigid synth. DNF search searches for these compatible regular expressions. It searches for regular expressions that have a lens between them using only syntax-directed rules. Rigid synth actually generates the DNF lens using the type-directed synthesis of the syntax-directed rules. It will find a lens between the DNF regular expressions if they are compatible. We have proven the correctness of our algorithm, so given two regular expressions, R and S, and a set of examples, if there is a lens that goes between the regular expressions that satisfies the examples, Optician will find such a lens. We've evaluated our tool on a variety of benchmarks. Our benchmarks require synthesizing transformations between two different formats. The synthesis tasks come primarily from Augeus, which is a bidirectional language used for expressing maps between Linux config files and C data structures. Because we do string transformations, we map between serialized formats of the data structures and the original config files. We also include some examples from FlashFill, which is a popular unidirectional string synthesis tool. And we also included some synthetic benchmarks to push our tool to the max. And lastly, we also included some ad hoc examples for places we thought that our tool would be useful, like mapping between bibtex and endnote bibliography files. Recall that our tool was designed to generate strict bijections. However, many of the formats we find transformations between are not actually in bijective correspondence. Two things cause this lack of bijectivity. The first is whitespace. So one format may have whitespace where the other doesn't allow it. So for example, one format might say lines cannot begin with whitespace, and the other format doesn't care about that. To resolve this, we allow for whitespace in formats where it's typically disallowed. So we would just remove the restriction that lines can't begin with whitespace. And the second cause of non-bijectivity is when one format lacks information that the other contains. So for example, one format might contain display name and last name, but the other format only has display name. So to synthesize a transformation between them, we need to project information. To address this lack of information in one format, we add additional fields saying projected information to the format lacking that information. So we would add that last name field. We tested R and some other string synthesis tools' performance on our benchmark suite. So on the x-axis is time, and on the y-axis is the number of benchmarks able to be completed within that time. So Optician's performance comes from three primary sources. So the first is that our tool only can synthesize bijections. This reduces the search space, but it also does reduce the expressivity of the individual functions the lens comprises. The second is that our tool uses format descriptions of the input format instead of just input-output examples. This makes the synthesis task much harder for them, especially on Linux configuration files where there's deeply nested iterations and disjunctions, which are hard to understand the format of. The other tools that only use examples have to not only synthesize the transformations, but also put in effort to understand the formats. Finally, our tool makes use of existing transformations in a process we call compositional synthesis. Using compositional synthesis, we can leverage existing lenses while synthesizing new ones. And in this way, it allows users to say subtasks and we think this allows our tool to scale to arbitrarily complex tasks. We've integrated our system with Boomerang in the main branch of Boomerang as of today. So you can say synth and then two regular expressions, and a input-output suite if you want to, and we will synthesize the transformation between those regular expressions. You can also then use that synthesized lens as you would a normal lens. So it can be used for future synthesis tasks, and it can also be used for just building up your own lenses manually. We have some limitations. In particular, we only handle bijective lenses. So while our system can be used to synthesize bijections, it can be used as a plug-in component for more complex lenses. So in the whitespace problem, the source format allows whitespace, the target doesn't. If we provide a canonization function that will canonize all the whitespace to one space, the normalized format will now be in bijective correspondence. So in this way, if we have these non-bijective transformations provided, then we can use our system as a plug-in component for synthesizing the overall transformation. So overall, we synthesized bijective lenses. We developed an algorithm for it and proved it correct. We evaluated this algorithm on a suite of benchmarks and found we were able to synthesize all of them in under 5 seconds. And we integrated our system with Boomerang, which is available at the URL. Any questions? So,
I'm going to repeat the question.
Oh, yeah. The question was, what is the main technical challenge with synthesizing non-bijective lenses? So for bijective lenses, the typing derivation is very, very strict. There's very few lens terms that map between two types. With non-bijective lenses, we can have very disconnected data structures, so it's hard to understand when it's correct to disconnect versus so have projections versus when to not have projections.
Can you unhook and then John will set up?
Yes.
In the back, please.
So, yeah, so because the lens, oh, sorry. The question was, what happens if you don't provide any input-output examples? I wish I included the slide in my backup slides, but typically you don't actually need any examples. And the reason for this is that the lens typing rules, as before, are very, very strict. So just finding a well-typed lens between the two formats typically will be the desired bijection. It's only for certain situations where you have swaps of very similar data that you'll need to actually provide examples.
So we're also going to take a question from the internet. For those of you who aren't aware, if you go to sli.do, you'll be able to ask questions anonymously about the talk. So one such example is, what about cyclic structures?
So the question is, what about cyclic structures? We only address Kleene stars. We think that as the kind of ways of having repeated data, we think that while I think many of our approaches can be generalized to different types of things, we don't actually address it in our format. And that's primarily due in large part to Boomerang, the lens language we use, only does typing on regular expressions, and so to integrate it, we worked on regular expressions.
Another quick question from the internet. In ambiguous cases, could you carry extra information so you could get exact round tripping?
In an ambiguous case, I guess I can't ask for a clarification. So right now we actually require that people give unambiguous regular expressions. So if that addresses your question, hopefully it does.
Let's take 2 more questions from the audience, and then we'll continue.
So you talked about how a pseudo-canonical form for these regular expressions, and it doesn't seem to, and there are certain things that are not covered basically on the Kleene star. Is you can have 2 identical regular expressions, but they're not made with specific canonical forms. Why is that? Isn't it generally true that you can have for EFAs a canonical form?
So the question is, why do we use this pseudo-canonical form instead of a canonical form like one that is generated from turning the DFA into a regular expression, or the minimal DFA into a regular expression? The issue with doing that is that sometimes you don't want them to be in canonical or in that form. So for example, let's say I'm trying to find, I only gave examples where the identity lens was really used, but consider when you're trying to find a lens between A star and epsilon or B A star. The A star will stay as A star when you do that transformation. Epsilon or B A star will stay as epsilon or B A star. You can't reduce it to just A star. So those two regular expressions stay incompatible. So we need to have this search through regular expressions still.
One last quick question.
Cogenerator generators like twig and verb and hyper have a similar flavor in that they're essentially defining languages that are related. They handle some degree of they handle the issue about there being multiple possible translations by use of weights as opposed to search or synthesis. Could you contrast what you're doing? I know there's a difference between strings and trees, but other than that, is there much difference between what you're doing with your lens languages?
I'm not familiar with those tools, so I can't answer that in an informed way, but I'd like to talk offline about it.
All right, let's thank the speaker one last time.